So, okay, perfect. So, hello everyone. I'm Awni Hannun. Nice to be there virtually with you, with the live and virtual attendees. So this is the tutorial on an introduction to automatic differentiation with weighted finite state automata. That's a mouthful, but we'll unpack it slowly over the course of this tutorial. So before we begin, there is a companion collaboratory notebook if you'd like uh, to join in. It's not really kind of a verbatim following of the presentation, but it does allow one to play around with some of the ideas that we'll go through, and I'll share some of the code that's in the notebook as well. So here's some of the setup code, and we can spend 5 minutes just for people to get set up for those that would like to follow along a little bit. The first step is to navigate to the link that's in this slide, the gist.github.com/awni. So I'll give everyone a minute to do that. Whoever wants to follow along, it's by no means necessary. I have a question. If there are questions during the tutorial, will I hear them? Okay. If there are questions during the tutorial, I'll follow along the chat. I assume that's where they'll show up. Actually, there's this raised hands. Okay, so questions from the audience are now turned on. So if people have questions, I think there should be a way for you to ask them. Feel free to jump in with questions. I don't mind at all during the tutorial. It's a long tutorial. Okay, so next slide. Once you've gotten to the gist, click the button to open it in the Colab notebook. You need a Google account for this. I'll give everyone a minute to do that. Okay. And then at the very top of the Colab notebook, there's a little setup cell. So if you click the play button, it will install the WFST software that I use, and it will import the relevant packages. So you can do that once, and it should have you set up for the duration of the Colab notebook. So like I said, this Colab notebook is not obligatory. It's just for fun to kind of play around with some of the ideas as we're going through them. You can see actual code and actually change and modify it and refer back to it in the future if you're interested in playing with these ideas more after the tutorial. Okay, so a brief outline of what I'd like to cover today. First, I'd like to motivate the reason we're interested in weighted finite state automata and specifically in automatic differentiation with them. So I'll talk about some of the ideas that led me to work on this and others as well, and why you might be interested. And then kind of so that everyone's on the same page, I'm going to go through the basics of automata. I'll start by describing the graphs, how these graphs work, what they represent. We'll discuss some of the core operations, not all of them, but some of them in detail to make sure everyone understands them. both the basic and slightly more advanced operations. And these are critical. It's like understanding matrix multiplication for tensors. You really want to make sure you understand these and have a good feel for what they do, because everything is built from them. After we go through the operations, I'll talk about actually how differentiation with automata works, and then how automatic differentiation with automata works. It's very similar to how it works with tensors. And then we'll look at some extended examples of two sequence criteria that are used in speech recognition and how we can represent them with graphs instead. So let's get started. So one of the kind of dichotomies in current speech recognition is this question of monolithic or modular. In the past, speech systems have been fairly modular. They've consisted of many components, all of which have been built by individual scientists and engineers over decades of accumulated experience. So you can see here kind of an example diagram of what one of those speech recognition systems looks like. And modular systems have benefits. I'll discuss a few of them, but they also have costs. On the other hand, the tide has really shifted towards these very monolithic systems, these end-to-end deep learning models. For example, in research right now, the best models are these transformer encoder-decoder models. It's basically one giant neural network with a lot of parameters, but not very much structure otherwise. So we're kind of competing between two ends of the spectrum, and there's an interesting question of, well, can we get the best of both worlds? First, though, let's talk about what is good and what is bad about monolithic and modular. So, in traditional software, modular is good because modular systems have reusable components, right? If you kind of build a module, you can use it in lots of different places. In speech recognition, an example of this would be like a language model. You use a language model in one acoustic context or another without necessarily having to retrain the model. You can also reuse acoustic models in different language contexts without necessarily having to retrain the acoustic model. If the acoustic model is just very good at predicting phonemes from speech, then it can be quite reusable. Monolithic systems, on the other hand, usually have to be retrained, or fine-tuned for every given domain because they attempt to do a lot more. They're not very modular. And that brings us to the second point, which is adaptability. Modular systems are more adaptable, usually because you only have to adapt a small part of the modular system, whereas the monolithic system usually requires a lot more data and fine-tuning or training for any given new domain. One of the downsides of modular systems is they're not as robust to errors. So because they consist of all of these components which have been put together and not learned to collaborate well and function as a cohesive unit from data, the errors in one unit can sometimes catastrophically propagate to other units and everything falls apart. In monolithic systems, errors, one part of the system kind of implicitly learns to be robust to errors from another part of the system. It's usually even hard to kind of draw lines within the system, but if there are errors from earlier layers, say, of the neural network, later layers can learn to be robust to those. So one of the nice things about automata is, in theory, and hopefully in practice, they can have all of these benefits. They can be reusable, adaptable, and robust to errors. The last one comes only if we actually use them to train our models. So for that, we need automatic differentiation. A couple more trade-offs between monolithic and modular systems. Monolithic systems learn from data. That's one of the reasons we love them. Now that we have lots of data, monolithic systems don't have this kind of glass ceiling in terms of performance, in terms of word error rates for speech recognizers, as we increase the amount of data, whereas modular systems do. On the other hand, it's much more difficult to kind of encode domain knowledge into a monolithic system. If I, as a researcher, say I'm a linguist and I know a lot about how language works and I want to encode that in a language model, or I'm a speech scientist and I know a lot about how audio works and I want to encode that in my acoustic model. It's very difficult to do that with a monolithic neural network. On the other hand, with modular systems, it's easier. It's almost kind of happens naturally as you're designing the modules. You encode the knowledge you have about the domain into how the module works. So we'd like that. We'd like to retain kind of the ability to encode prior knowledge into the system, while also having the ability to learn from data. And I believe automata offer us a path towards this. So in the past, automata and currently are used in speech recognition, and especially in production speech systems. And the way that they're used is mostly at what we call decoding time. So you kind of train your different models. You have your acoustic model, you have your language model, you have your lexicon. All of these models are trained individually in isolation. And then they're represented, or their outputs are represented as WFSTs, as transducers, and combined in a decoder. And this step where we kind of convert them to WFSTs and then combine them in the decoder, it only happens when we're using the speech system, not when we're training it. And that's a missed opportunity. And it's also a problem because, like I said earlier, it means it means that the components haven't learned to work together as cohesively. And so there's potential robustness issues and potential performance to be had. So why do we want differentiation with automata? Because it lets us combine training and decoding. So that picture I just showed you of all those FSTs being combined only at decoding time, well, we can actually combine them at training time if we can, especially if we can use automatic differentiation with them. Another benefit, kind of a more pragmatic benefit of combining training and decoding, is that it's really nice to only have one code path for how your system works, right? If you implement the training and the training algorithm, and then you have to re-implement kind of a completely different approach for decoding, there's a lot of opportunity for bugs to be introduced in the translation. There's also just wasted effort. So combining training and decoding has this other very pragmatic benefit, which believe me is a real consideration. Like in doing the translation from training to decoding, there's almost always bugs that happen. Another benefit of differentiation with automata is this idea of separating data from code. In this case, the data is the graph, and the code are the operations on graphs. The graphs being automata. And in general, whenever you separate data from code, it makes it easier to express ideas. And the same thing is going to happen with automata. If we can separate the operations from the graphs, then all of a sudden we open up this really rich design space of ideas that we can express. And you'll kind of get a flavor of that more towards the end of the tutorial when we start to encode some of the criteria, the sequence criteria in graphs. You'll see how much easier it is to do. Although I think just to give you a little bit of a flavor of that early, I'm going to kind of explain how that works at a high level. So don't worry too much if the details of this slide don't make that much sense. We'll get more into it towards the end of the tutorial. But the basic idea is that we can represent, loss functions that we use to train speech recognizers, for example, as the operations on two different graphs. One graph is this graph A, which is a function of the input speech and the target transcript. And the other graph is this graph Z, which is a function only of the input speech. And so we can compute the probability of the transcription given the input speech by operations on these two graphs, the operations that I've shown specifically in this slide. So if we do things this way, we can represent lots of different criteria. We can represent, the automatic segmentation criterion. That's one we used at Facebook a lot. In live to letter, we can represent CTC. That's one that we used in deep speech and is used a lot in production speech systems these days. You can represent lattice-free MMI, also used a lot in production speech recognition systems, all kind of in the exact same form that I just showed you as the difference of two graphs. So I kind of, just to give you a flavor and inspire some interest, went and looked at a few of the more popular implementations of CTC, the loss function used to train speech recognizers, and counted the lines of code for the different implementations. So Warp CTC, WAV to letter, PyTorch, these are all kind of custom, very optimized implementations of CTC. And if you look at them, they have in the thousands of lines of code. This is because, implementing these for the GPU especially, which requires a lot of careful optimization, is non-trivial. Now, if you implement the same algorithm in an automata-based framework with automatic differentiation, the code that's specific to the algorithm is only 30 lines. And this is almost 2 orders of magnitude reduction. So that's a big deal, in my opinion. I mean, of course, there's a lot of code that goes into the general part of the framework, which is powering the algorithmic specific part. But the good thing about that is all of that code is reusable. It can be reused for other algorithms. So any optimizations that you do that improve CTC improve other algorithms potentially as well. So this is really a potentially very powerful concept. And the other benefit of this is that the same graphs that we used for training can also be used for decoding. So now you have a single kind of code path where you don't necessarily have to re-implement your decoding algorithm from your training algorithm. So there's another kind of nice way to think about automata, which I think helps build intuition for those that are relatively new to them, and that's to compare them to tensors. And so, this is a slide which you can kind of come back to every now and then and look and see as you get more familiar with the operations on automata, which operations they're kind of similar to with respect to tensors. So as an example, like intersect and compose for automata is kind of similar to matrix multiplication and convolution for tensors. The shortest distance operations, the forward and viterbi scores, are kind of similar to reduction operations on tensors. And you see there's a couple others on this slide. So perhaps these analogies aren't as clear now, but as we go through the operations and you kind of come back, you'll see that they are kind of similar, and then it helps you kind of keep track of what these different operations are doing, what they're intended for. For example, compose, like I said, is kind of similar to matrix multiplication. When you multiply two matrices, you say you have a matrix A, a matrix B. The elements of the matrix C are kind of the sum over this inner variable K, AIK, BKJ, as you see in that first line. So with composition, we have a very similar high-level form. When you compose a graph A and B to get a graph C, the score of two paths in the graph C is represented as the accumulation of the score over this inner path R in the graph A and the graph B. So you're kind of, in both cases, you're summing over some inner variable to get the output in the new graph. And so the analogy is really kind of nice there. Okay, so that's it for the introduction. I'm going to take 1 minute to see if there are any questions, give people a second to think about things, and please do let me know if you have any questions so far. So I see that there might be a question from Peter. Hi. Peter, I don't hear you too well, unfortunately. Would you mind chatting your question? Okay, well, I don't see your question in the chat. I'm not sure if it... Okay, let's see. Hello. A little bit better. Why don't you try your question? Unfortunately, your audio is too broken. I'm sorry, Peter, I can't hear you. If you're able to chat your question, please go ahead and I'll follow the chat. I'm not sure if, hopefully the chat will show up in my chat window. If it doesn't, then yeah, we might be out of options. Okay. I'll keep an eye on that if a question shows up. Let's move on. So, hi, Lars, is there a question? Yes. I don't see the question in the chat, unfortunately.
So he asked, his question was, what does LSE mean? I think in the slide before.
Okay.
In the
good.
That's
so
the question.
So let me ask you a question, Lars, before I answer that. Is it okay if so? Is there any way for me to see the chat from the participants, or?
I don't know. I'm not sure.
Okay.
So I just clicked underneath ask a question, and when I click on ask a question or chat, maybe now I can't see it anymore because I'm in this other view now.
Okay. Well, let me answer Peter's question, which is, we'll definitely get into what LSE means more specifically in later part of the tutorial, but it's basically the operation log sum exponentiate, which is the notation that I use for the forward score of the graph. And I will discuss that in quite a bit more detail later in the tutorial. Are there any other questions? Okay, so we'll continue. So this is a hierarchy of the graphs that we're going to be discussing. So this hierarchy is a hierarchy based on representation power. So in the inner square are the graphs which can represent the least general kind of sequences. And these are just generic finite state automata. And they have two varieties which are equivalent in their expressive power, but not in the kind of the size of representation, which are deterministic and non-deterministic. And then slightly more expressive are the same automata, but when you allow weights on the edges. And then even more expressive than that are what we call weighted finite state transducers, which are the most expressive graphs that we'll cover in this tutorial. So just so everyone's on the same page, super simple finite state machine. It has nodes with state labels 0, 1, 2, has edges with transition labels A, B, C. And these state machines can be deterministic or non-deterministic. A non-deterministic state machine just means that from any given node, you can have edges with the same labels leaving that node. So if you look at this non-deterministic automata from state 0, you have two arcs, both labeled A, leaving state 0. That means that it's ambiguous kind of which arc to follow. Or another way of interpreting it is you follow both arcs at the same time. It's non-deterministic. In general, the graphs, the automata we're going to cover, they can be non-deterministic. So it's important to understand that that's the case. So this is the simplest kind of graph that actually is quite important to us. So this is a weighted acceptor. And the notation, or the kind of the graph notation we're going to use, is that the start state of the graph is in bold. So the 0 here is the start state. The accept state of the graph is the concentric circles. So the 1 state is the accept state. And any given arc is labeled with the arc label / the arc weight. So the label between 0, 2 with the A has a weight of 0. The label between 2, 1 with the A has a weight of 2. Now, if you want to compute the score of, say, a given sequence, you can score any sequence. Some sequences have scores. Some sequences have non-zero scores. Some do not. But if you want to score, say, the sequence A, then you would just follow the arcs. So you take the first A, the arc from 0 to 2. Then you take the second A, the arc from 2 to 1. If you're in accept state, then the graph accepts the sequence AA, and the score that it gets is 2, because you sum the arc weights along the path for that sequence. Cool. So now, for those of you that got the Collaboratory Notebook up and running, you can actually kind of go in and construct this kind of an acceptor. I'll kind of go through what this code means for the first time, but I won't go through it every time. So basically, first you define your symbol mapping so that you know kind of what the integer IDs of the labels are. That's just useful for drawing the graph. It's not really useful for anything else. Then you actually construct the graph. So you instantiate an actual automata. You can add your start node, you can add your accept node, and then you can add just any number of interior nodes. And then you add arcs. And the arcs, each arc has a source node, a destination node, and a label, and potentially an input or an output label, which we'll discuss when we get to transducers, and a weight. So then you add the arcs, and that makes this graph here. Great. So an acceptor and a transducer can have multiple paths which represent the same sequence. in this graph, you see that the path AA, or the sequence AA, has two paths which accept it. So you can go from 0 to 2 to 1, or you can go from state 0 to state 3 to state 1. Now, if you want to score the sequence AA, you have to consider both paths. So for the first path, the score is 0 plus 2. For the second path, the score is 1 plus 3. The way that we combine the scores of paths for our case is using this log sum exp operation that there was a question about earlier. So you take the LSE log sum exp of 2 and 4, and that gives you, some number, which I can't do in my head, something close to 4. Okay, so that's how that works. Now, acceptors and transducers, and I should say that this is a bit of a matter of taste. Some of these graph kind of properties they're a bit of matter of taste. Like you can say that acceptors and transducers can have multiple start and multiple accept states, as I do here. And the GTN framework that we're using to construct automata with automatic differentiation allows for this. In other implementations, graphs can only have a single start state, but they're equivalent in their expressive power because of other properties, which let you represent a graph with one start state as a graph with multiple start states as a graph with one start state. And I'll kind of show how that's done a little bit later. So like I said, a graph can have multiple start and accept states. So take a look at this graph. And the question is, what is the score of the sequence AB? So just think about how would you compute the score of the sequence AB based on what we covered on the previous slide. I'll give everyone half a minute to think about that. So there are two paths in this graph which accept the sequence AB. And that's because there are two start states. So the first is the path from start state 0 to state 2 to state 3. And the second path is from start state 1 to state 3 to state 4. And then we combine those scores with the log sum exp operation. Good. So transducers and acceptors can also have self loops on nodes. They can have cycles. So this graph, it can accept a lot of sequences. One example of a sequence or a set of sequences it accepts is the sequence A star BB, where the star is kind of the usual regular expression, meaning 0 or 1, 0 or more copies of A. And so that's because of the self loop on the state 0. So in general, self loops and cycles are okay, but they do introduce complexity, and some operations will not work or are not supported for self loops and cycles, which I'll mention later on. Now, one of the more important concepts in acceptors and transducers is this notion of epsilon transitions. They're also kind of one of the more slippery concepts, more subtle, to really gain an intuition for what they enable. But the basic premise is that an epsilon transition is one that can be followed without consuming any input. And so this graph here, it accepts two sequences. One is the sequence AB, but it also accepts just the sequence B because you can transition from 0 to 1 without consuming any of the input. So for an acceptor, that's what an epsilon transition means. You still have to accumulate the score. So, if it had a non-zero score on the epsilon arc, you would still score that when you're scoring the sequence B. So in the GTN framework that we're using in the Collaboratory Notebook, you can add Epsilon transitions with this GTN.epsilon special symbol. And so you just set the label equal to GTN.epsilon. So let's get a flavor for what epsilon buys us. So I mentioned earlier that you can represent a graph with multiple start states with a graph with a single start state. So how would we go about doing that using epsilon's transitions? And also, while we're at it, we can represent a graph with multiple accept states with a graph with a single accept state. So maybe think about that for a second, and we'll look at how it can be done. So the basic premise is straightforward. So you just add a new node, a new start node, and epsilon transition from that start node to all the old start nodes in the graph, which are no longer start nodes. You do the same thing with the accept nodes. You add a new accept node and epsilon transition from all of the old accept nodes to the new accept node, and the old accept nodes are no longer accept nodes. And the weights, this is kind of important when the graph is weighted, have to be 0 because you don't want to accumulate weight following those epsilon transitions. So this graph is actually equivalent to the previous graph. And by equivalent, we mean that it accepts the same set of sequences and assigns them the same weights. But it only has a single start state and a single accept state. So that's how acceptors work. Now we'll go into this generalization of acceptors called transducers. Now transducer is like an acceptor, except instead of just accepting an input, it converts an input sequence to an output sequence. So this is a simple weighted transducer. You know, the start state and accept state are the same. Now on each arc, instead of just having a label / weight, you have a input label, colon, an output label / a weight. And whenever you take transition across an arc, you consume the input label, you output the output label, and you accumulate the weight. So if we think about the score of a sequence, we no longer think of just an input sequence. We have to think about a pair of sequences. And we say that the transducer transduces one sequence to another. And the score of that transduced sequence, so in this case, AB transduced to XZ, is found by taking the score of each arc along the path which transduces it. In this case, it would be the first arc in between 0 and 1, and then the arc between 1 and 2, for a total score of 3. So in GTN, the code, you know, the transducers and acceptors are represented by the same data structure. Really, the only distinguishing criteria from a transducer and an acceptor is that the input label and the output label are not the same in a transducer. And so this is kind of why a transducer is a generalization of an acceptor, because if you want to represent an acceptor with a transducer, you just have a transducer where the input label and output label are always the same. So another question for you to think about: what is the score of the sequence of the transduction of the sequence AAB to ZYY in this graph? So think about that for a second to make sure you kind of understand how the transducers work. In the meantime, if there are any questions, I'm happy to answer. Please raise your hand, figuratively, virtually. Okay. So to score the transduction of AAB to ZYY, you know, we look for all the paths which transduce the pair, and we find that there are 2. We follow the state sequence for the first, we follow the state sequence for the second, accumulating the arc weights. Turns out they both have the same score, 6 and 6. We take the logarithm exp of those two scores, and we get the final score of the transduced pair. Okay, that's it for basic operations. Or sorry, that's it for acceptors and transducers. Now we'll go into some of the basic operations. Let me see if there's any questions. Okay, Maxim. Hi, Maxim, do you have a question? Go ahead.
On the last slide, when you computed score for ABB to ZYY, it seems that the second path has another output sequence. Am I right?
The second path has another output sequence. Did I miss one?
Yes. You have shown the two paths, two possible paths.
Yes.
They both have the same input sequence, but different output sequences.
Oh,
ZYY
no.
or ZZY?
No. So let me go through it more carefully and tell me if it's wrong. Okay. So the first path from 0 follows the self loop. So the output is Z, and then it follows the arc from 0 to 2. So the output is Y, and then it follows the arc from 2 to 3. So the output is Y. So you have the output ZYY on the input AAB. Now the second path goes straight from 0 to 1. So the output is Z. Then it goes from 1 to 3. So the output is Y. And then it goes from 3 to 3. So the output is Y again. So you have also the output ZYY. So for both paths, you have the same input and the same output. And someone please jump in if that doesn't make sense. Thank you for the question. Okay, so we'll cover 3 basic operations with transducers. Oh, there seems to be a question. Hi, Peter, do you have a question? Oh, unfortunately not. We're still broken. Your audio is still broken. Maybe you can do the same chat question. Maybe Lars from earlier can interpret your question over chat. I'm very sorry. Unfortunately, I can't hear you. If anyone's able to see Peter's question on chat, that would be very helpful. I'm unable to see how to do that in my my view of the interface. Okay, well, I'll continue with the operations until I hear otherwise. So closure is also called the Cluny star operation, or the Cluny closure, basically computes an output graph from an input graph. And if the input graph represents a sequence, say the sequence ABA, as in this graph, then the closure represents 0 or more copies of the sequence. So by 0 copies, we mean it accepts the empty string, the empty sequence, epsilon, or the sequence copied 1 time, 2 times, so on and so forth. And if the graph accepted more than one sequence, then we'd do this for every sequence that the graph accepts. So to compute the closure, we use Epsilon transitions, and Epsilon transitions make it quite easy to compute the closure. So you add a new state to the graph, which is both a start and accept state. And that's how we accept the empty string. We epsilon transition to the old start state. And then when we get to the accept state, we can epsilon transition back to the beginning. And that's how we represent the fact that we can kind of accept arbitrarily many copies of any of the sequences of the input graph. Oh, and by the way, the closure is denoted by this star operation. So when you have the input graph A, and then you raise it to the star, that means compute the closure. And this is what it looks like, and it should look like in the Collaboratory Notebook. You construct the graph in the beginning, and then you call this one-line command gtn.closure, which takes the graph as input and outputs the closed version of the graph. Union is another of the basic operations. So if you have three input graphs, say A1, A2, and A3, the union accepts any sequence which is accepted by any of the input graphs. Looks like there's a question. 1 second. Hi, Lars, do you have a question?
We do it for each of the paths. Would it also allow one path followed by another path, or would it only allow the same path?
Yes, good question. It allows one path followed by another path. So
okay, thank you.
Yeah, as a concrete. Oh, go ahead.
And to what Peter, I think he wrote in chat before, that when we are in this view, we can't see the slides. So you answered the other question about the different output and input sequence when we didn't see the slides.
Oh, I'm sorry. So I just changed the view
to follow.
When you say the view, I didn't change the view on my end. What do you mean by that?
So now we can see the slide. So when you talk to somebody else, often it comes these big windows with the camera, and then we can't see the slide. Now we can see.
Sorry, I don't see that on my side at all. It all looks the same. That's unfortunate.
Okay.
Okay. Please let me know if that causes problems in the future.
Okay. Thank you for asking my question.
Yep.
Answering.
Yep, of course. So to be clear, Lars's question was, let me give an example of what it means. So if the input graph, say, accepts the sequence AB and also the sequence AA, then the closure could accept, say, the sequence AB, AA, AB, AB, AA. It doesn't have to be only copies of AB or only copies of AA. It can be kind of any interleaving of the two. So like I was saying, the union accepts any of the sequences that any of the input graphs accept. And the score will be the score kind of accumulated from all of the input graphs. So the way that we represent the union is with this sum operation. So A1 plus A2 plus A3. Now, and the graph itself is just the same graph, but instead of being three individual graphs, is a single graph with three start states and three accept states. So this might be a little confusing. It looks like the left and right sides are the same, but there's a subtle difference in code. One is represented as three separate data structures. The other is a single data structure with three start states, three accept states. And you can tell because the state nodes increase consecutively in the union, whereas on the left side, they start over from 0 for each of the input graphs. So in code, what this looks like is you can construct each of your 3 input graphs or any number of input graphs. And then when you go to compute the union, you use this operation gtn.union, and it takes as input a list of graphs and returns the union. And so this list can have one or more graphs. The union of a single graph is just the graph itself. Okay, the last of the basic operations is concatenate. And concatenate, as it sounds, takes 2 graphs and computes the concatenation. If there is a sequence, say BA, accepted by the first input graph, and a sequence, say AC, accepted by the second input graph, then the concatenated graph would accept the sequence BA-AC. Now you have to do this for every input, every sequence in the first input, and every sequence in the second input. So, when you think about how many paths the concatenated graph accepts, it's the number of sequences of the input graph, the first input graph, times the number of sequences in the second input graph. Because for each pair in the 2 graphs, that can be a sequence that is a sequence in the concatenated graph. Computing the concatenation is also especially easy with the use of epsilon transitions. You just put an epsilon from every accept state of the left input to every start state of the right input. That gives you the concatenated graph. And again, in code, this looks very similar to union. You construct your input graphs, and then to compute the concatenation, you call gtn.concatenate, and it takes a list of graphs, which can be 1 or more. And the concatenation of the single graph is just the graph itself. Okay, here's a question for all of you to think about for a minute. What is the identity graph for concatenation? And by the identity graph, it's like the number 1. If you multiply by 1, you get the same number back. If you concatenate by the identity, you get the same graph back. What is the identity graph for concatenation? So the identity graph for concatenation is the single state, or is the graph which accepts the empty sequence epsilon. And that's because if you concatenate any sequence with epsilon, you get that sequence back. So this graph here is one graph which accepts the empty sequence epsilon. It's not the only possible graph, but it's the simplest. And this state is both a start state, the circles are bold, and an accept state, the circles are concentric. And so that means that this graph accepts the empty string, epsilon. Okay, here's another question. What is the annihilator graph for concatenation? So annihilator is like the number 0. When you multiply a number by 0, you get 0 back. When you concatenate a graph by the annihilator graph, you should get the annihilator back. So what is the annihilator graph for concatenation? So the annihilator graph is the graph which does not accept any sequences. And it's an important distinction from this graph and the graph which accepts the empty sequence. The graph which does not accept any sequences doesn't even accept the empty sequence. It accepts nothing. So it has no accept states, or no accessible accept states. And one possible representation of that is this graph here, which is just a start state, nothing else. And the intuition is that when you concatenate, if you can't concatenate anything, if you have an input graph and you have nothing to concatenate with, then you're left with nothing. Another question. Let's just be super familiar with concatenate. So what sequences does the concatenation accept? And maybe even more simply, how many sequences does the concatenation of these two graphs accept? Think about that for a few seconds, and then I'll show how it works. So the concatenated graph is represented here. As you see, every accept state from the first input is connected to every start state from the second input with an epsilon transition. So since there were two accept states in the first input and two start states in the second input, there are 4 new epsilon transitions. And the concatenated graph accepts the 4 sequences below. Okay, that's everything for basic operations. So we covered 3 basic operations. We covered closure, Cluny star, we covered union, and we covered concatenate. And now we'll go into the kind of perhaps more important advanced operations, but also more difficult to understand easily. First, let's see for a few seconds if there are any questions. Okay, moving on. So it's my opinion that the most important operation with transducers is intersect. And this operation is intersect and compose are kind of the same operation. Intersect is for acceptors and compose is for transducers. So when I say intersect, I really mean intersect and compose. And if you remember from the beginning, this is the kind of the operation that I made an analogy to matrix multiplication with. And it really is, in a way, kind of as matrix multiplication is central to tensor-based operations in, say, deep learning, intersect and compose are central to transducer-based operations in differentiation, automatic differentiation with transducers. So I think it's especially important to understand what the intersection does and a little bit in terms of how to compute it. So intersect, if you have 2 input graphs, the intersected graph, as the name suggests, would contain only those paths which are contained in both of the inputs. So if the sequence is accepted by the first and by the second, then it will be accepted by the intersection. The score in the intersection is the sum of the scores from each of the input graphs. And we denote the intersection by this open circle. So the intersected graph is A1 circle A2, where A1 and A2 are the inputs. So here's a very simple example. If I have the input A1 on the left, the input A2 on the right, and their intersection is represented by this graph here. So, the input A1 accepts the sequence AB, and it turns out that's the only sequence that A2 also accepts. So the intersection accepts only the sequence AB. And the state labels will kind of understand what those mean when we talk about how to compute the intersection, which we'll do right now. So I'm gonna walk through kind of some pseudocode for how the intersect algorithm works. If the pseudocode isn't super clear, well, ask questions. I'm happy to explain, but I'm also going to go through a more pictorial representation of the algorithm directly afterwards. And that might make clear what was not so clear in the pseudocode. So I'll go through both. Maybe some will follow one and some will follow the other. Hopefully the two will be complementary. So the way that the algorithm works is you have a queue, a FIFO queue, first in, first out, and you have your new graph, which is the graph we're trying to compute, the intersection of the two inputs. So the first step is to initialize those. The second step is for all possible pairs of start states in the two inputs, those are potential start states in the intersected input. And we also add them to our queue as states to explore. Then we pop the next state pair from the queue and we explore it until the queue is empty. If that state pair, so one state from the first input, one state from the second input, if there are any arcs leaving each of those states with matching labels, then we take the destination nodes of those arcs and we construct a new state pair, V1, V2. And for that new state pair, we add it to our queue and add it to our intersected graph if we haven't done so already. And we also add a new arc in the intersected graph where the label is the label that the two arcs matched on, and the weight is the sum of the weights of those two arcs. So, if you don't understand this algorithm, it's kind of hard to understand just by reading it. One thing to note is it's actually pretty short. It's not that complicated, but it's very powerful what intersect does. So let's actually try to understand how this algorithm works pictorially. Maybe this will be a helpful exercise. So again, we're trying to compute the intersection of A1 and A2, the same two graphs which we looked at earlier. And we start with this empty queue. Now the first step that we said was to take the pairs of start states. So in this case, there's only one such pair, 0, 0. We add it to our queue and we construct the corresponding node in the intersected graph. So now we have one state in our queue and one node in our intersected graph. So we pop the state, the first state in our queue. So now we're exploring that state, 0, 0. From there, we look at all kind of pairs of outgoing arcs. We find the pair with the label A that matches, and the downstream nodes are 0, since this is a self loop, and 1. And so we add the state pair 0, 1 to our new graph as a state, but also to the queue as a new state to explore, since we've never been in that state in the new graph before. So now our queue has just the state 0, 1, and we're exploring state 0, 0. Let's see if there's any more arcs that we need to explore. Okay, so it turns out there is another arc pair that matches on the label B. So we add that arc pair, we add the downstream nodes of those arcs, so the state pair 1, 1 to the new graph, We also add it to the queue since we haven't seen it before. We add the arc with the label B. Now we look to see if there's any more matching arc pairs from the state 0, 0 that we're currently exploring. If we look, we'll see that there aren't any. And so what that means is we're done exploring the state 0, 0. There's nothing to add to the queue. So now we'll pull the next state pair from the front of our queue, in this case 0, 1. From 0, 1, from the state 0 in the first graph, the state 1 in the second graph, we look to see if there are any arcs with matching labels. In this case, there are. There are the arcs with the label A, which lead us to the state 0, 2. Since we haven't seen that state before, we construct it in our new graph and we add it to the queue. We look again to see if there's any other arcs with matching labels. Again, we find there are 2 arcs with the label B, and we add the downstream nodes of those 2 arcs as a new state pair in our intersected graph. The only thing to mention here, the important thing to mention here, is that since the state 1 in the first input graph and the state 2 in the second input graph are accepting states, then the state 1, 2 in the intersected graph is also an accepting state. So we have to make sure we denote it as such. We look to see if there's any more matching arcs from the state 0, 1. There aren't, so that means we're done exploring 0, 1. There's nothing to add to the queue. We pull the next thing from the front of the queue, 1, 1. Are there any arcs leaving 1, 1 which match? Well, that's not possible because the state 1 in the first graph has no outgoing arcs. So there's nothing to add for that state. It's easy, we're done exploring it. Pull the state 0, 2 from the graph. And again, we look to see if there are any outgoing arcs with matching labels. Again, this one's easy because there's no arcs leaving state 2 in the second input graph. So we're done exploring that state pair. And another important point is that since there's nowhere to go from the state pair 0, 2, it's a dead end. And we can also just remove it from the intersected graph. So we just do that. Now, finally, we get to the last state in our queue, 1, 2. We look to see if there's, again, any arc pairs which are matching. Turns out neither one has any outgoing arcs. There's nothing to add. But since this state is an accepting state, we have to keep it in our intersected graph. At this point, our queue is empty. And so the algorithm terminates. We're left with the intersected graph. So in the Collaboratory Notebook, if you want to compute the intersection, you construct your 2 input graphs, first one and the second one, and then you compute the intersection. The intersection just takes 2 inputs. If you want to intersect 3 graphs, you can do it, but you have to make 2 calls to the intersect. Okay, so that's how intersect works. Now compose, as I said, is almost the same operation, but for transducers instead of acceptors. So what does it mean for transducers instead of acceptors? Well, if the first input graph transduces x to y, the second input graph transduces y to z, then the composition transduces, this is a typo, sorry, the composition transduces x to z. So they match on the inner label, and the composition transduces the outer sequences. And the path score in the transduced graph, or in the composed graph, is the sum of the scores from the 2 input graphs. So it'd be, you'd score X arrow Y in the first input graph, you'd score Y arrow Z in the second input graph, and you'd add their sum, you'd add them up, and that would be the score in the composed graph. So here's an example, which I won't go through in detail, but it's good to kind of, maybe after this tutorial to look at this slide and actually kind of compute the composition by hand, because it will really help you to understand what the composition is doing. If you take the first input and the second input, you can kind of work out the composition. It shouldn't take too long, and you'll get the graph A1 composed with A2 below. So there's another important point with both intersect and compose, and that's that you can have epsilon transitions in either of your input graphs. And the way that epsilon transitions are handled in intersect and compose is a bit subtle. Sorry, it looks like there's a question. Give me 1 second. Hi, Peter, is there a question? Yes.
Oh, great. I have a question for you. What is the difference between how do you intersect and compose? The question is that do I understand correctly that if I have a transducer that has this on all arcs have the same input labels and output labels, so the input labels and the output labels on both graphs are the same. So are the results of compose and intersect operations equivalent or not?
Yes, good question. So the answer is yes, they are equivalent. And the reason is because if the input labels and output labels are all the same, if you kind of go back to this slide, which has a typo, then when you're matching kind of by the transitive property, when you're matching on the inner label Y, you'll also be matching on the outer labels. So if Y equals Y in the input and output in the first in the two input graphs, then X will also equal Z. And so you end up getting the fact that X and Z are going to be the same, have to be the same, basically. Are there any other questions? So compose with epsilon. So as I was saying, epsilon can be quite subtle with composition and intersection. I'm not going to go into all the subtleties because it's actually quite complex and not so necessary for this tutorial. But to illustrate how it works, if say we have the input graph here on the left, A1, and in the middle, A2, and we want to compute the intersection. Well, usually the intersection would just have one arc, which would be the arc with the label A. But since the input graph also has this epsilon transition, then you can also optionally follow this epsilon transition in the first graph. So now you would have to construct the epsilon transition in the intersected graph. And so basically, during the exploration phase, when you're exploring from the state 0, 0, instead of only considering arcs with matching arc labels, you can also consider arcs from either input graph, which have an epsilon, without considering an arc from another of the input graphs. So here's an example of how to intersect two graphs with an epsilon, where the first one has an epsilon. So, because of the epsilon transition, the intersection of these two graphs is not empty. So the first graph accepts the sequence AB, the second graph accepts the sequence AB as well. So this, the intersected graph also accepts the sequence AB. But importantly, the epsilon transition is preserved because it has the score of 1.5. And so we need to account for that when we're scoring the sequence in the intersected graph. Okay. The second set of advanced operations, which are perhaps the second most important kind of group of operations with automata after intersect and compose, although some might argue that they're more important, are what kind of are often grouped as shortest distance or shortest path algorithms or operations. We're not going to use the graph terminology. We're going to use kind of the speech recognition terminology. The graph terminology is usually reserved for when one wants to do more general things with graphs. But in our case, we're always going to either do the forward score, the Viterbi score, or the Viterbi path. And so we're just going to use those three names for the operations. And so specifically, the forward score of a graph is represented as this LSE, log sum exp, of the input graph. And what it does is, if you think about it, what it's actually doing, though it's not how it computes this in practice, is it delineates all possible paths accepted by the input graph, computes the score of each of those paths, and then accumulates those scores with the log sum exp operation. Now, the Viterbi score does almost the exact same thing, but instead of accumulating the path scores with log sum exp, it accumulates them with max, or it takes the max over all of them. So the log sum exp, the forward score and the Viterbi score are almost the same, except you switch the operation which you reduce the path scores with from a log sum exp to a max. And the Viterbi path, which we'll represent by the argmax of the graph, is just the highest scoring path in the graph. And when there's a tie, it just breaks ties randomly. So one thing to note is the Viterbi score is unique, and there's only one score, which is the maximum. But the Viterbi path isn't necessarily unique. There can be lots of paths which achieve the highest score. We just want one of them. There's a nice analogy from these shortest distance operations to tensors. So the forward score, it's like a soft maximum. Specifically, it's like a log sum exp over a vector. It's the kind of analogous to that. But if you think about what that's doing, it's like taking a soft maximum. Instead of looking for the max and extracting it, you have this log sum exp operation, which kind of approximates the maximum as the maximum gets more and more distinct. The Viterbi score is actually like a maximum, and the Viterbi path is like an argmax. It's like the index of the maximum scoring item in the tensor, but in this case, it's the path in the graph. So you can kind of keep this table in mind when thinking about these operations, and it should be easy to kind of figure out which one is which. So let's talk about how to compute these, or first let's talk about, well, let's do an example. What is the forward score of this graph? So, and what is the Viterbi score of this graph? So the forward score and the Viterbi score both rely on the scores of all possible input paths or accepted paths. So the first thing we do is we delineate each of the paths and we compute their scores. So you see this graph accepts 3 paths, and the reason it's 3 is because it has 2 start states, 0 and 1. So there's 3 paths which are accepted, 3 sequences, and we compute each of their scores. Now to get the forward score, we simply take the log sum exp of each of those path scores. That gives us something close to the maximum, but not quite, a little bit larger. The Viterbi score is exactly the maximum, 5.3. And the Viterbi path is the path which achieved the maximum. So in this graph, it's the path from 0 to 2 and from 2 to 3, which gave us the score 5.3. Now we'll represent the Viterbi path as a graph itself. It's always going to be this chain kind of graph where, it's just linear from one node to the next. But we'll represent it as a graph. And that will make it easier to do things like differentiate through the Viterbi path operation. So in the Collaboratory Notebook, if you want to compute these scores, it's fairly straightforward. You can construct your input graph as usual. You can add some weights to your input graph to make these scores more interesting. So the way that this works is, your weight list should be as long as the number of arcs you added to the graph. The first weight will correspond to the first arc you added, the second weight corresponds to the second arc, so on and so forth. So this is a weighted graph with these weights. Then we call GTN forward score, which gives us the forward score, or LSE of all the paths. We call GTN.Viterbi score, which gives us the maximum of all the path scores. And then we call GTN.Viterbi path, which returns the graph which represents the Viterbi path. So to compute the Viterbi score and forward score and also the Viterbi path, I mentioned kind of delineating all possible sequences accepted by the graph and then scoring each of them individually. Of course, this is not practical. If you have a large graph, you can have kind of combinatorial explosion in the number of paths or sequences accepted by the graph. So it's not practical to just delineate each of them, compute its score, sum them all up with log sum x, or take the max. So instead, there's this kind of beautiful dynamic programming algorithm, very kind of classic dynamic programming, which you'll see as called the kind of the Viterbi algorithm or the forward algorithm, which basically makes computing these scores very efficient. The complexity is basically linear in the number of nodes in the graph, assuming that the graph is acyclic. So the way that Viterbi score works is, if say we're at the state 3 in the graph and we want to compute the Viterbi score of all possible paths starting from a start state in this graph, which end in the state 3. So this is just kind of a sliver of some possible graph. This is like a little cross-section or slice of a graph. And say that, there were a bunch of paths that started off here and ended up in this state 0, a bunch of paths that started off here and ended up this state 1, same for the state 2. The Viterbi score of all possible paths from start states to state 0 is 3.1. To state 1 is 2.8, and to state 2 is 4.7. So that's what those numbers represent there. Now, if I want to get the Viterbi score of all possible paths from any start state, from out here to the state 3, I just look over all incoming arcs. I add the weight of the arc to the Viterbi score of the source node of that arc, and I look for the one that achieves the max. In this case, it's this arc with the score 6.1 from this node with the score 2.8. So the Viterbi score of all possible paths from any start state to the state 3 will be 2.8 plus 6.1. In a more general sense, if we are at this state in the graph, and we want to compute the Viterbi score to this state from all possible start states, then we just look at any incoming arc to this state, and we ask the question, which arc has the largest weight plus Viterbi score of its source node? So we take the max over all arcs of the weight of that arc plus the Viterbi score of the source node of that arc. And that's what this notation here means, the S source E. The source of E sub I is the source node of the arc E sub I, and the S is the Viterbi score, and then the W is the weight of the ith arc. So we're just asking the question again, of all the incoming arcs to this node, which one gives us the maximum, where we're taking the maximum over the weight of that arc plus the Viterbi score of the source node of that arc. And that gives us the Viterbi score up to this node. And then to get the final Viterbi score of the graph, we just ask this question for the accept node of the graph. Now, log sum x is the reason I showed you Viterbi is because it's a little bit simpler to understand. And then the generalization to log sum x is nice. So instead of, you literally switch a max for a log sum x. Instead of asking the question, what is the maximum, you take the log sum x of all of the incoming arcs, the score of the source node of that arc plus the weight of that arc. So then if you just, you kind of just do this operation at each node in the graph once, and you're done. So that's why this algorithm runs linearly in the size of the graph. The only thing you have to be careful of is that you have to go in a topological order, which is why the graph has to be acyclic. You have to start with graphs without any incoming arcs, and you can only compute a node score once all of the input node scores which feed into that node are available. So that's, you see that you need this source E sub I score to be available. Let me see if there are any questions about that. It's a little bit subtle. I'll give everyone a few seconds to think about it. Okay, good. Let's keep going. So for the Viterbi path, so the Viterbi path is basically a matter of bookkeeping. So as we're computing the Viterbi score, as we go through kind of this topological traversal, at each node. Is there a question? I'm sorry, I don't hear very well. Very faint.
Ne, řekni mu to. Spell the question box, please.
Are you referring to me? Are you talking to me? What was the comment? Where's the question box? Oh, I see. Oh, I see. Okay, got it. Okay. Yep. No, I see it. Yep. Okay. Are there any past? Oh, I'm sorry. I hadn't seen this question box. Okay. Yeah, my mistake. Okay. So, first of all, are there any paths to support n-best path? Any plans to support n-best path determinization minimization? Yes. This is a good question. I assume you mean in the GTN framework. we'd like to do that. We're working on minimization, for example. Determinization, I mean, all of these algorithms are kind of priority will be based on need. So if there are, if there's the ones that are needed most will be the ones that we kind of prioritize implementing the soonest. The graph contains several paths with maximum score. Will the Viterbi path graph contain all of them? The answer to that is no, it will just return one randomly. Okay, and then Jan, I see your comment about the break. I think I'll get to a point soon, and then we can take a 5-minute break for everyone to take a restroom break or something like that. Probably right after the Viterbi path discussion. Again, my apologies for missing this question box. I didn't realize that that was there. I'll pay more attention to that from now on. Okay, so the Viterbi path, as I was saying, is mostly a matter of bookkeeping. As we're computing the Viterbi score at each node, we just have to remember which arc achieved the Viterbi score. So that's what these red arcs represent here. Each of the red arcs is the arc which, to that node, achieved the Viterbi score. And then when we get to the final accept state, if we kind of traverse backwards following these red nodes, or sorry, these red arcs, that will give us the Viterbi path for the graph. So these are kind of often referred to as back pointers in dynamic programming. You just have to keep a record of which kind of arc achieved the maximum as you're going forward to a back pointer. And then when you're done, you just traverse those back pointers and you get the Viterbi path itself. Okay, so let's see, there's a question from Peter. Let me take that question, then we'll take a break. Hi, Peter, do you have a question? Hello? Okay, I don't hear the question. I'm happy to answer it now or after a break. But why don't we take a 5-minute break? So I'll resume at 38. So I think 16:30, actually 16:39 for you all. So let's say 39. So everyone go ahead and take a 5-minute break. I'm also gonna take a 5-minute break. Thank you. All right, everyone, let's resume where we left off. So actually, I see there's a couple of questions. Let me answer those for the group first, and then we'll pick up with differentiation with automata. So the questions are from Peter. What happens if the graph is cyclic? Is there going to be an error or an infinite loop? With the, I assume that's with respect to the Viterbi and forward operations. And specifically for those operations, if the graph is cyclic, the GTN framework will throw an error. It will raise, I think, an invalid value error or something. In general, certain graphs with cycles, you can actually compute the Viterbi and the forward score. There's some certain technical conditions, which if they're met, it's possible to compute the forward score of a cyclic graph. But we don't do that yet in the framework. It's not commonly needed. Do these operations work on the GPU? Second question. Not yet, but that's coming. So, so actually I didn't mention this in the beginning. There's another framework which does very similar, which is very similar to GTN, developed at about the same time. It's called K2, and also it's from Dan Povey and company. Dan Povey being one of the creators of Caldi, and K2 is it supports some of the operations that GTN supports on the GPU. I think in general, it's more optimized than GTN, but perhaps maybe a little bit more verbose, less easy to use for the general case. Okay, so let's continue with differentiation with automata. Okay, so so we have these operations. So we have, say, an operation like concatenate. If we have an input graph A and input graph B, we can compute their concatenation AB as shown in this slide. And now we'd like to think about, well, can we compute derivatives with respect to this operation? So what does that even mean? Well, if say we have the arc weights of the concatenated graph, I would like to know what is the derivative of one of those arc weights with respect to one of the arc weights of the input graphs. And I'd like to know that for all of the arc weights of the output graph with respect to any of the input graphs. So specifically, if say I have C sub 3 in this concatenated graph, how sensitive is C sub 3, the arc weight, to infinitesimal changes in, say, B sub 1 in the second input graph, or in, say, A sub 2 in the first input graph? So that's what we mean by derivatives of with respect to operations on graphs. So it's really about differentiating arc weights. Okay, so let's actually look at this example. We can actually kind of compute the derivatives for this example. So for this example, there are only 4 non-zero derivatives, and they are all of the value 1. If you think about it, that's because there's only 4 arcs in the concatenated graph, which are influenced by arcs in each by only 1 arc in only one of the input graphs. So let's say take C sub 1. That arc weight comes from A sub 1. So the derivative of C sub 1 with respect to A sub 1 is just 1. A small change in A sub 1 leads to the same magnitude change in C sub 1. That's why the value is 1. The slope is 1. C sub 5 comes from the arc weight B sub 2, and the derivative is 1 because a small change in B sub 2 leads to the same size change in C sub 5. Right? If B2 was 3 instead of 2, then C sub 5 would be 3 instead of 2. So the slope is 1, any changes in C sub 5 exactly reflect changes from B sub 2. So those are the non-zero derivatives. Now, there are also zero derivatives. So for example, if we want to get the derivatives of C sub 1 with respect to all of the other input arcs, those will all be zero. So C sub 1 is not influenced by changes in A sub 2, it's not influenced by changes in B sub 1, and it's not influenced by changes in B sub 2. Any changes in those arc weights will not change C sub 1 at all. The slope is zero, the derivative is zero. So that's how differentiation for concatenation works. Okay, so now let's take a look at this example, closure. I'll give everyone to think about a second. What are the derivatives of the output arc weights for the closure, this graph specifically with respect to the input arc weights? And perhaps the simplest way to think about it, and the simpler way to phrase the question is, what are the non-zero derivatives? So I'll let everyone think about that for a second. Okay, so with the closure, in this specific one, this specific example, there's two non-zero derivatives. It's because there's only two arcs in the input graph. Now, if we look to see where did arc A1 end up in the output graph in the closure, we see that it led to arc, W sub 2. So the derivative of W sub 2 with respect to A sub 1 is 1. And the reason the value, the derivative, is 1 is because any change in A sub 1 is exactly reflected in W sub 2. If we increase A sub 1 by a number, by some value, then we increase W sub 2 by the same value. W sub 3 came from A sub 2, so that the derivative of W sub 3 with respect to A sub 2 is also 1. And then if we want to know the rest of the derivatives, well, they're all zero. And there's 1, 2, 3, 4, 5, 6 of them. So, let's look at an example. W sub 1, the arc weight associated with this epsilon, well, the epsilon is a new arc in the output graph. It didn't come from any arcs in the input graph. So its derivative with respect to all of the arcs in the input graph, A sub 1 and A sub 2, are 0. The same is true for W sub 4. For W sub 2 and W sub 3, they're 0 with respect to the arc which they did not come from, and 1 otherwise. So you can see that computing the derivative of the weights of the output graph with respect to the weights of the input graph, it's often kind of a matter of bookkeeping. Which arc did the output arc come from in the input graph? And so if you know that, then you know which of the derivatives are non-zero or 1, and otherwise, and then the rest are 0. So intersect, in the same way, we can say, say we have an input graph A and input graph B, and we compute the intersection, A intersect with B. Now we'd like to know what is the derivative of all of the arc weights W1 through W7 in the intersected graph with respect to either of the arc weights in each of the input graphs. So in this case, each of the arc weights in the output graph come from two arcs, one in the first input and one in the second input. So say like W sub 1 in this graph will come from one arc in A and one arc in B. So it should have two non-zero derivatives. And the rest, the derivative with respect to the rest of the arcs will be 0. And the same is true for all the other arcs in this graph. So concretely, if we want to know, say, what the derivative of the ith arc in the output graph with respect to the first input, A, then we just look to see which arc it came from. That derivative is 1, and it's 0 otherwise. So as an example, let's take W sub 1 and do it completely. So W sub 1 in this graph, you see it connects the state 0, 0 to 0, 1. So that means in the first input, it came from this arc, 0 to 0. In the second input, it came from this arc, 0 to 1. And so W sub 1, the derivative with respect to A sub 1 is 1. The derivative with respect to B sub 1 is also 1. The derivatives with respect to all of the other arcs in both of the input graphs are 0. And that's how differentiation with intersect works. So in this case, each of the output arcs comes from two arcs, one from each of the inputs. And so each of the output arcs will have two non-zero derivatives, which will be 1, and the rest will be 0. Are there any questions about that? So I just did 3 examples of how we can compute derivatives with respect to these graph operations. The other operations are similar, like compose, union. The forward score is a little bit more complicated, but relies on the same principles as, same kind of differentiation, same ideas of computing derivatives of outputs with respect to inputs. So the next thing I'd like to discuss is how we can actually take this idea of being able to compute derivatives with respect to graph operations and do it automatically. And then, as we'll see in the last part of the tutorial, once we can do this automatically, we can start to do kind of really fun and interesting things. We can express ideas quite easily. So, for those of you familiar with, say, PyTorch or TensorFlow, but especially with PyTorch, because that's how the automatic differentiation of GTN, that's where it was inspired from, should be familiar with how automatic differentiation, you should be able to quickly pick up how automatic differentiation with automata works, and specifically in GTN. So let's say that we have this, this sequence of operations, or this composite function. Let's assume that A1 and A2 are 2 input graphs, and we'll let them be parameters. And by parameters, I mean they have weights that we'd like to learn in our algorithm. And X is another input graph, which is the data. So in contrast to the parameters, it's fixed, but it's still an input. So then we compute this function, this kind of composite function on these 3 inputs. Take the union of A1 and A2. We take the closure of the data X. This is just some made up function, by the way. It's not supposed to be anything practical or even interesting, but just to demonstrate how automatic differentiation works. So then we take the union, the closure, we intersect them, and then we compute the forward score of the intersection. We can represent this function as a graph, distinct from an automata. This is the compute graph. with the figure below. And so what you're seeing here is, you have your every circle is a graph or an intermediate graph, a temporary graph. So the solid circles are the input graphs, and the dashed circles are the graphs which are kind of constructed as the output of different operations. And the reason they're dashed is because they're not actually kind of, well, they're not input graphs. They're intermediate graphs. And then the rectangular shapes are the operations. So every operation takes one or more inputs and produces a single output graph. And then we can kind of represent this function as this sequence of graphs interleaved with operations. So once we have the compute graph, we can then compute the derivative of the output graph G4, the final output, with respect to any of the inputs. Specifically, we'll want the derivative of the output graph G4 with respect to A1 and A2, since those are the parameters. And then we can use those derivatives in, say, something like stochastic gradient descent to learn the parameters of those graphs. So I'm not going to explain how the automatic differentiation works in detail. I think the high-level bit is that it's reverse mode automatic differentiation. So you construct this graph dynamically by computing this function. The graph is actually represented explicitly by the runtime, the GTN runtime. And then once the graph is computed, you can request to compute the derivatives. And since it's reverse mode, it will go backward through the compute graph, computing derivatives in a backward topological traverse of this compute graph. And so as an example, say that we want the derivative of the output G4 with respect to the input A1. Well, once we have computed the derivative of the output G4 with respect to the intermediate graph G1, we can use that to compute, along with the chain rule of differentiation, essentially, same idea as backpropagation, to compute the derivative of the output G4 with respect to the input A1. And so the equation kind of, in terms of graphs, looks like this. It's not super critical to understand, but the principles are almost the same as with tensors, except instead of elements, entries in tensors, we have arcs on graphs. And instead of kind of familiar tensor operations, we have these graph operations, but the derivatives are, as we went through earlier, they're not that complicated. So let's look at how this works in code. So if you have the Collaboratory Notebook, now's a good time to go back to it and look into it in the section on differentiation with automata. So the first thing we do is we make our parameters. So we construct the graph A1 and the graph A2. The important point is that since these are parameters, it means we want gradients for them because we want to learn them. And so we have to specify that the gradient should be calculated. That's what that argument calc _ grad equals true is for. For the data, we don't need the gradient, so we specify that it's false. I think false is the default. I forget off the top of my head. I think false is the default, though. So you don't have to do that. And it's not an error to request the gradient for x. It's just not necessarily, it just won't be very efficient. The framework will compute it and you won't use it. So it's just wasted computation. So that's how we specify kind of that A1 and A2 are parameters and x is the data, by whether or not we request the gradient. then we compute our function. So, we take the union of the two parameters, we take the closure of the data, we intersect those, and then we compute the forward score. And then that gives us the output graph G sub G4. And if we want the derivatives, we call backward on the output graph, which does the reverse mode automatic differentiation. And so that will compute the derivatives. And now if we want to access them, well, for any graph for which the gradient was requested to be calculated, such as A1 or A2, we can access its grad method, and that will return the gradient. Also, for any of these intermediate graphs, we can access the grad method. And for these intermediate graphs, they will have gradients if any of their inputs require gradients. And so we'll do that recursively. So for example, for G1, since A1 and A2 both requested gradients, G1 will have a gradient. G2, since X did not request a gradient, we won't have a gradient for G2 either. G3, since G1 requires a gradient because A1 and A2 do, G3 will have a gradient. And then G4 is the output. The gradient we also represent as a graph. And so, just like the gradient of a tensor is a tensor of the same size and shape, the gradient of a graph, of the gradient of an output with respect to an input graph, is a graph of the same size and shape. The only difference is that the arc weights represent the derivatives instead of the weights of the arcs themselves. So in this graph below, we've overloaded notation here to show like the derivative of the graph with respect the output graph G4 with respect to the input graph G1, A1. The arc weights here will be the derivative of, say, the first arc, the output graph, the arc of the output graph G4 with respect to the first arc of this input graph. Okay. So that's it for automatic differentiation and differentiation with automata. Let me take a couple minutes to see if there's any questions, and then we'll move on to the next part of, and the last part of the tutorial. Let's see. Peter. Hi, Peter. Do you have a question? Yes.
How does the gradient graph is going to look like?
Right. So right now, well, first of all, we wouldn't call that a gradient technically. We would call it a Jacobian. Just like with tensors, when you have vector-valued functions instead of scalar, so when the function goes from vectors to vectors, you no longer are dealing with gradients, you're dealing with Jacobians. And so the Jacobian of a function which takes a vector and outputs a vector will be a matrix, where each entry in that matrix is the derivative of, say, the ith entry of the output vector with respect to the jth entry of the input vector. Now, the Jacobian of graph functions is the same idea. And specifically, I've been a little bit sloppy in my speech. The gradients that I was showing earlier in the section on differentiation with automata were actually Jacobians. We're showing the entries of the Jacobians. But so the Jacobian for an output graph with respect to an input graph will be it will be, it will have kind of, for each arc in the output graph, there will be an entry for all of the arcs in the input graph. Now, currently, so that's the kind of the theory. The practice is the backward function in this code. Right now, it doesn't compute Jacobians. So it assumes that the output graph only has one arc. And so that will be the case. So basically, the way to think about it is it assumes functions are scalar output functions. And so it computes gradients. And the same idea is the case with PyTorch. When you're computing a gradient, you're doing backward. You're assuming your loss function is one value, and you compute the gradient of that one value with respect to all of the input tensors.
Okay, that's great. Thank you.
Any other questions? Oh, I see in the questions list. Sorry, it doesn't automatically scroll. Okay. Let me answer these. Okay, so what is the complexity of computing gradients of forward score over arc weights? The complexity of the forward score gradient is, in terms of asymptotic complexity, is the same as the forward direction. So it's linear in the size of the graph. Second question from Jan. I'm wondering about the differences between the forward and backward algorithm. Could you please contrast those? Oh, I see. Okay, yeah. So this is a good question. So in GTN, there's this backward function, and then there's the forward score. And there's actually a reason we called it forward _ score instead of just forward. And that was because in speech recognition and kind of in related problems, there's this algorithm called the forward backward algorithm, where you use to compute the forward score and the used to compute the forward score. And we wanted to distinguish the forward score, which is the forward algorithm, from backward, which is the function which differentiates automatically the compute graph. And so that's an important distinction. These should not be confused. They're two completely different concepts. GTN.backward on a graph is how you compute the gradients of the compute graph, and forward _ score is how you compute the forward score of the graph. The last question in the questions list is the closure on X just for illustration or usually needed? It is just for illustration. That entire computation was just for illustration. As far as I can tell, it's not useful for anything other than to illustrate the idea of the compute graph. Thank you for the questions. Sorry, I missed those. This question feed wasn't automatically scrolling. Okay. So last section, sequence criteria with automata. Okay, so finally we're able to do some. Sorry, is there another question? Sure.
Can you hear me? Excuse me?
Yes.
Could you go back one slide, please? My name is Peter. I wanted to ask about one more, please. I wanted to ask about if the gradient is a graph, then when we are looking for a situation when it gets nullified, what would be the zero I'm looking at in here algebraically? Like if I want to find a way to to minimize this? Am I trying to make this to select directions in which I can make this graph get closer to a zero, which would be a non-accepting FSA, or like an empty FSA?
Yes. No. So good question. So actually, in optimization, for example, what one usually does as a stopping criteria is look at the gradient. When the gradient vanishes, it means you're at a local optima, or a saddle point, but hopefully an optima, and then you can terminate. So we can do the same thing. So when you're doing that with tensors, and you have, say, a vector of derivatives, you'll look at the norm of say that vector, and as it gets close to zero. We can do the same thing with graphs. So instead of looking at a vector of entries, you can kind of just interpret the arc weights of the graph. You can kind of just unroll them and compute the norm of that sequence of arc weights. So I hope that answers your question. So you would treat the graph just like you would kind of treat an n-dimensional tensor. You would just unroll it, compute the norm of all of those entries in the gradient, and as that norm gets close to zero, then you would know that you're reaching a critical point.
Yes, thank you.
Okay, so sequence criteria with automata. So let's look at a specific example. So I'm first going to go through this criteria. It's called the automatic segmentation criteria. And the reason I started with this, it's not the most popular. We used it in WAV to Letter at Facebook. It's not the most popular sequence criteria, but it is relatively simple and easy to understand. And so that's why I'm starting with it. And then as a second example, we'll look at connectionist temporal classification. So let's say that we have an input, we'll call it capital X, and it has 5 time steps. So the way to think about this is X could be the speech. It has 5 frames. The output Y is the sequence AB. So Y is the transcription. Now, what we'd like to do is to compute a probability, a conditional probability of Y given X. Why do we want this probability? We want it because, well, for one, we need to score Y given X in order to know how to improve our model. So if we have examples of Y and X, then we want our model to assign high probability to those examples, low probability to everything else. But we also want this model, P of Y given X, because, the real reason is because when we don't know Y, we can then search for Ys which are most likely given a specific value of X. Now, if a user speaks into their phone, I can find the transcription, which is the most likely thing that they said. So I want to compute this conditional probability. Now, what we need to do that is for each frame of the input, I need to compute a score, and I'll take the product of all of those scores to get the overall conditional probability. But my output Y only has 2 tokens. It's only of length 2. And my input has 5 time steps. It's of length 5. Oh, sorry. I see, sorry, again, this questions is not automatically scrolling. Okay. Or maybe there's just a lot of latency. I'm not sure. Okay, anyways, I answered that question already. So, since the output only has 2 tokens and the input has 5 time steps, it's not clear, like if I want to compute this score and I need 5 different scores, what should I put for each of these? Like, should this be an A? Maybe. Should this, should the next one be an A? Should it be a B? I'm not sure. So the automatic segmentation criteria specifies a set of allowed alignments. it says for any given output, you can align it to an input by either repeating any of the output tokens one or more times. So let's look at a couple of examples. So for this example we were looking at previously, the set of allowed alignments of the output y equals AB to an input of length 5, you can see some examples of allowed ones in the first column. So AAABB, because you have the repeats of A and then the repeats of B. A followed by 4 B's is okay. 4 A's followed by a B is okay. So those are some examples. And then in the second column, we see some examples of not allowed alignments. And let me just briefly say why these are not allowed. So in the first example, this corresponds to the output sequence ABA. In the second example, this corresponds to the output sequence AB, but it only aligns to an input of length 4. So it's too short. In the last example, this corresponds to the output A. It's not the right output sequence. So we have this set of allowed alignments that ASG specifies. With an alignment, so given any specific alignment, I can compute its score. So right now we're just looking at this is just math, not with graphs, just with like vectors as usual. So if I want the score of an alignment A, I take the sum of the individual scores of each of its entries. So if you look back at those alignments, of length 5, for each one of those, I get the sum of the score of each one of those to get the overall score of the alignment. So now I have a function which takes as input an alignment and also the input audio or input X and produces a score for that alignment. And the key idea with ASG and CTC, one of the key ideas, is that instead of computing the conditional probability of y given x by assuming a single alignment between them, we marginalize over all possible alignments that we've said are allowed. So we have a set of allowed alignments. We sum over all of them. And so that's what that first term represents in the conditional probability. And so when I say when we sum over them, we're in probability space. So we actually do we're in log probability space. So we actually do a log sum exp over the scores of the alignments. And then we normalize so that we get a valid probability by the score of all possible alignments of length 5, which are unconstrained by the output. So there's, all possible sequences of length 5 or of the same length as the input would go into that second term. So that's the normalization term. So let's look at how to actually compute this in code, set this up. So for the output y, let's go back to our example. We had y equals AB. We can construct what I call a target alignment graph, or sometimes a target constrained alignment graph. And so this graph, A sub y, it represents the fact that with ASG, you're allowed to repeat each token an arbitrary number of times. You must include it at least once, though, in any given alignment. So that's what this graph represents. You see the self loop. I can repeat it any number of times, but then in order to get to the next state, I must actually observe that output. Same for the B. And so this is the code which constructs that graph. So that's how I make the target alignment graph for the sequence AB. Then I also need what we call the emissions graph, the graph E. And the emissions graph represents our, say the output of something like a neural network, or really any machine learning model, which takes as input which takes the input X as input. And so, what this graph represents is if the input is 4 time steps, if x has 4 time steps, each one of these each one of these slices between 2 consecutive nodes represents the score. So there's, so let me take a step back. So we have an alphabet, say ABC. Let's say that our alphabet is ABC. Our output token set is ABC. And for each time step in our input, we need a score for every possible output in our output set for each of A, B, and C. That's what the emissions graph encodes. So for each time step in our input, this is the first time step, we get a score for all possible output tokens in our output set, A, B, and C. This is for the second time step, third time step, fourth time step. This is called the emissions graph. And these scores come from, say, for example, a neural network. So the neural network takes as input some speech, and for each frame it produces a prediction of some scores for all possible output tokens. So this is just an example of the code here on the right of how we can construct that, where the logits are in this case random, but normally they would come from some kind of a model. And the linear graph construct here is part of GTN because it's something that comes up over and over again. So it has this kind of helper function to make a graph which looks like this. Now, if I want to represent the set of allowed alignments of AB to all possible of AB to an input of length 4, the way that I do that is by taking the intersection of the target alignment graph A sub y with the emissions graph. And that intersection, which you see in the bottom of this slide, if you look at it carefully, you'll see that it represents all possible alignments, as I said, between AB and the input of length 4. And not only that, if you follow any given path in this graph, the score of that path represents the score of the corresponding alignment, given the emission scores in the emission graph. So now I have this input and output constrained alignment graph, A sub xy. So that's the main idea. So now now let's go through the actual function in detail. So, it's like 10 lines of code. They're powerful lines, so it's not easy to understand, but it's very short. So once you do understand what these lines are doing, you can start to do some really amazing things by only with small changes. So ASG, so the simplest version of ASG takes as 2 inputs the emissions graph and the target constrained graph A sub y. The first step, as we just said, is to compute the intersection of those 2. And so for that, we get the input and output constrained graph A sub xy. And then the emissions graph will be used directly to compute the normalization term. The next step is to compute the forward score of both the input and output constrained graph A sub xy and the emissions graph. And so the intuition of what we're doing in this step is for the first forward score in this line, we're delineating all possible paths, all possible alignments of the target y to the input of length whatever. We're computing the score of each of those alignments, and then we're summing them up. Since we're in log space, we're doing a log sum x, and that's why we're using a forward score. That's what's happening in this line. And then in this line, we're delineating all possible sequences that are the length of the input, unconstrained by the target. So just any sequence which is of the length of the input, and computing the score of that sequence and accumulating them with log sum x. So now we have the numerator, A sub xy score, the normalization, and then the next step is Since we're in log space, we subtract them and then negate the subtract, and then negate that to get a negative log likelihood, so that we can minimize it. But the basic idea is that you're just dividing one term by another in probability space. So you're kind of normalizing the score of the target alignments by the score of all possible sequences. And that gives you the probability of the target. And then the real power of the framework, with automatic differentiation comes in at this point when we want to compute gradients. So we clear the gradients, any old gradients on our emissions graph, and then we call backward to get the gradient on our loss. Let me see. It looks like there is some questions that just showed up. So, okay. Question from Jan. Does GTN support some kind of lazy operations? Might be useful for some operations that have a tendency to blow up, like intersection or composition. The short answer to that, Jan, is no. GTN does not yet support lazy operations. The reason for that is because at training time, typically when you do an intersection, is followed at some point by a forward score. And to do the forward score, you usually need the whole graph. And so we're not doing anything fancy like, forward scoring a graph, which can be kind of partially fit in memory, but partially on disk. And hence where lazy operations would make sense during training time. And since training is kind of the main motivation of GTN, not decoding, training is like the reason we built GTN as opposed to using existing FST frameworks. Lazy operations haven't been a big priority, but that's something we're thinking about is how to deal with really huge compositions. And the answer honestly is not clear. Like that's a research question in my opinion. And for those of you that are lucky enough to have time to work on research, is an interesting research direction. Question from Peter: why do you need the normalization term? Why can't you just maximize the probability of the correct alignments? Oh, this is such a good question. That is important. The answer to this question is important to not just automata and this specific example. Why do we need normalization terms in general? Well, let me say first that the normalization term is not the only way. It's not the only way to do this. But if you don't have a normalization term, if you just try to maximize the score of the target, you can have what's called kind of mode collapse, where the model can just maximize everything. It can just output a high score for anything. And that's not good because it's not discriminative. So what you need the normalization term for is the intuition is you need to increase the score of the things you care about, but decrease the score of the things that you don't. If you don't do this decreasing part, then the model can find a degenerate solution just by giving everything a high score, and then it's not useful. Now, the normalization that we use here is one way of doing that. There are other ways, like negative kind of sampling, for example. But the normalization is the most commonly used. For example, if you look at a cross entropy loss or logistic regression, that's exactly what they're doing. It's just a lot simpler in those cases. Are there any other questions? Okay. So let's keep going. So we were at automatic gradients in the sequence criteria with automata. And so like I was saying, so, once you've computed the loss, you clear the gradient on the emissions graph, and then you can just call backward on your loss, and that will compute the gradients for the graphs for which you requested it. And those gradients will be accessible. So this is just basically one line of code to get gradients, which is really nice. If you look at some kind of custom implementations of ASG, the part of the code which computes the gradients is like, you know, a few hundred, sometimes more lines of code. So the ASG I've been describing so far is a simplified version. It's basically a transition-free version of ASG. Now, the actual version that was kind of written about in the original research paper has transitions. So it has, for any given alignment, not only does it assign a local score for each output token in that alignment, but it also assigns a transition score. Oh, sorry, there's a question. So what is the computational complexity of the intersection of the E graph with the alignment graph, especially in the case of large alphabet and big number of frames? Okay, and the large number of frames. So the computational complexity of that intersection algorithm, it does not depend on the size of the alphabet. So that's good. And it does, and in terms of the number of frames, it depends linearly on the number of frames. So if you have, you know, if your input increases, if the length of your input increases, then the length of the runtime of the intersection with the emissions graph will increase linearly. In general, the computational, the asymptotic complexity for that intersection depends on the length of the output times the length of the input. So the product of those two. So that's kind of where you should pay attention in order to make sure that your computation times aren't exploding. However, so now that I've said that, this version of ASG with transitions, actually the size of the alphabet matters. So now the computational complexity does depend. Yeah, so okay, so next question. In a normal training setup, for example, in the CTC loss in PyTorch, is the normalization term built into the loss function? The answer to that question is actually, well, so in PyTorch CTC, I believe the answer is no. The normalization is not. Now, this is kind of a subtle point. So with CTC and transition-free ASG, you can take a shortcut. So when you're computing this conditional probability, instead of separating the, so let me go back actually to the code. Instead of computing the normalization term as the forward score of a separate graph, it turns out that you can normalize the emission scores locally at each time step. And then you get the equivalent, and then you can basically ignore the normalization term. So basically, there's an equivalent way to compute ASG where instead of kind of separating out the normalization term into a different graph, you normalize the local scores of the emissions graph at each time step. And then you can just use the forward score of the constraint graph. These are mathematically equivalent. Like, you know, it's the exact same thing in this case. And so with PyTorch CTC, the way that you use it is you softmax, you normalize your emissions at each time step prior to calling CTC. And so that's the equivalent of, you know, doing what this code does. But it's not as general because not all loss functions admit that that simplification. And so that's why I've shown you the more general approach here, because as we'll see with transition-free ASG, or with ASG with transitions, we actually have to compute the normalization term explicitly. So with transition ASG, we add these transition scores to the score of any given alignment. So we also have this function h, which assigns a score for a sub t and the previous output token a sub t minus 1. So now all we've changed is how we score a given alignment, and everything else is the same. So we've just added these transition scores to how we score a given alignment. Everything else is unchanged. Now to get the conditional probability of y given x, we just sum over all possible alignments, log sum x over all possible alignments, and then we subtract our normalization term. So how do we do this in graphs? Well, we can represent our transition function or transition model as a graph. And that's what this graph shows here. We'll call it B, and it's a bigram transition model, which means that it assigns scores for a token and the previous token. And so what this graph represents is, say, I'm in state A, and I see an output B. Then when I follow that arc, I get the score probability of B given A, or the transition score of B having previously seen A. So the state that you're in represents the history, and then the next output token and weight represent the score of that output token given the history. So that's what the transition graph looks like. And I can use that transition graph. Well, so one more point about the transition graph is we usually encode the fact that there's a start of sequence token, just to denote the fact that we score at the beginning. You need a history for the beginning of the sequence as well. And so that's what the graph actually looks like when you include a start of sequence tokens. So now there's one start state, and you can transition to all of the initial tokens from that start state, and then from there the graph is the same. So now ASG with transitions, if I want to include those transition scores, it's quite simple. And so what it looks like is my function now takes as input, instead of 2 graphs, it takes 3 graphs. We've added the bigram transition model. And then when I want to compute the score of all the target constrained alignments, I just have to intersect with the transition graph at some point as well. And then when I want to compute the normalization term, I have to intersect the transition graph with the emissions graph. And that gives me the score of, when I compute the forward score of that gives me the score of all possible sequences, where each score includes both the emissions from the emissions model and the transitions from the transition model. So you can see in barely 3 lines of code changed, I've all of a sudden done this very powerful thing of including a transition model. And so that's the reason I've shown this code in its general form with the explicit normalization term. If you were to look at an implementation of ASG, the part that handles the transitions is non-trivial. It's you have to write a lot of code to handle transitions. Here, once you've constructed the graph, which isn't so difficult, the actual core function is barely changed at all. And not only that, there's nothing in this code that says B has to be a bigram transition model. It can be a unigram transition model. It can be a trigram. It can be an arbitrary n-gram. Of course, computation complexity and sample efficiency matters, but there's nothing in this code that's specific to the fact that B is a bigram. So, we've got this really general function now that can use an arbitrary n-gram transition model, which is really demonstrating the power of working on graphs here. And then typically I'll want the gradient of my transition model as well. And so I'll clear the gradients of the emissions graph and the transitions graph. And then when I call backward, those will be computed. Okay, looks like there's more questions. So why is it necessary to intersect EPS X with B in the normalization graph? Why not just EPS X? So I think by EPS X, you mean the emissions graph, and B, the transitions graph. So the question is, why do we do this line here? Why do we intersect the transitions graph with the emissions graph in the normalization term? And the reason for that, why don't we just have the emissions graph on its own? The reason for that, if you look here, when I'm computing the normalization term, I need to score all possible sequences, all possible alignments that are of the same length as the input. But now an alignment score, as we showed earlier, it has to include the transition scores. So even in the normalization term, the alignments have to include the transitions. If we didn't, then it wouldn't be properly normalized. So that's why we have to intersect the transition graph with the emissions graph, because all possible alignments in the normalization term also have to include the transitions. Okay, so we're going to move on to the last section on CTC. I think I have enough time to cover it. It's not very long. And let me just make a meta point now, which is some of this stuff with sequence criteria is a little bit subtle. And I think it's especially important to understand. That's why I spent a lot of time on the core operations like intersect, concatenate, closure, perhaps not enough time on the forward score, but still a decent amount of time. I think, the really understanding those operations will make it easier to understand what, when you see these kind of dense lines of code like intersect on multiple graphs, what they are doing. And so then kind of going back with that understanding and then working through these in more detail, actually visualizing some of the graphs, looking in the Collab notebook that I have where you can play around with these functions. I think you'll be able to develop an understanding for these. Looks like there's another question. So, okay, so two more questions. Let me take these questions. So could a transition model be more complex? For example, I could create a word level n-gram in a graph that computes model units to words with a lexicon, compose them and use it as a transition model. So yes, the answer is a transition model can be more complex. You can do things like this. This is actually one of the main benefits of, this is one of the main motivations of differentiation with automata. You can have a word level transition model. You can have a word piece level acoustic model, or otherwise different model, and then you can combine the scores for both into your criteria. The main problem, the main challenge, is computational complexity. So when you start to compose these really big models like a word level n-gram, which can have a lot of words, things get expensive. And so that's kind of where the research, that's kind of where the edge of research is right now in this area, I would say, or where one of the frontiers of research is kind of, we want to do things like that. That's why we built this framework, to make it easier to express those kinds of ideas. But things get to be really slow really quickly. So we need to figure out kind of clever ways of making it faster. Next question, is intersection associative like matrix multiplication? Intersection is associative like matrix multiplication. Intersection, unlike matrix multiplication, is commutative. However, compose is not commutative. So compose is really analogous to matrix multiplication. So compose, like matrix multiplication, is associative. Like matrix multiplication, it's not commutative. So think about these, actually, if it's not clear. Why? I'll let you all kind of puzzle these out. And the last thing that's also very similar to matrix multiplication is that even though it's associative, the order that you do the operations can make a big difference in the efficiency. If you multiply three matrices, you know, there's often an order to do it which is much faster, and then one which is much slower if you're dealing with kind of irregularly shaped matrices. The same is true with composition. If you compose three graphs or intersect three graphs, it often makes sense to intersect two of them first and then the third in terms of computational complexity. Okay, so let me breeze through CTC, and then I don't know if we'll have time for questions at the end, but let's see. So ASG has a couple of problems. One is the problem of repeats. So if I have an alignment like AA 3Bs and then an A, there's a problem with this alignment is that I don't necessarily know what output it represents. It could be ABA, it could be AABA, it could be ABBA. Like I don't know whether or not I should collapse the A's. I don't know if I should collapse the 3Bs into 2Bs or 1B, or should they stay 3Bs? So we just don't know how to deal with repeat tokens without ambiguity. The other problem with ASG is the problem that in certain cases, I might like to represent the fact that an input frame doesn't necessarily need to correspond to an output in the alignment. So far, we've been showing that every input has to correspond to some output alignment token. But sometimes it's nice if there's a way for an input frame to not correspond to an output token. And so CTC solves this problem with kind of one fell swoop by introducing the notion of a blank token. And this blank token is really the abstraction which converts transition-free ASG to connectionist temporal classification. It's the primary difference. Everything else follows from it. And so the blank token, the semantics of it are that it is required between consecutive repeats. So if I had a sequence like AAB, there would have to be a blank token between the two A's. Otherwise, it's optional. And then in alignments, you're allowed to have any number of blank tokens in between or at the beginning and end of any of the output tokens. So let's say I have the output sequence y equals ABB, and I have an input sequence of length 5. So on the left, you see 3 examples of allowed alignments, and on the right, you see 3 examples of not allowed alignments. And so, you know, on the left, you see that, for example, the blank token always has to be between 2 Bs because they're consecutive repeats in the output. So there's always a blank token in the set of allowed alignments. And in the not allowed alignments, let's just talk through why those are not allowed. In the first row, this corresponds in CTC to the sequence AB. Since there's no blank token in these Bs, they all collapse into a single B. This corresponds to the sequence AB again, because there's no blank token between the Bs. And this corresponds to the sequence AAB, because there's a blank token between the 2 A's. So all of these are the wrong sequences. Now, so the target alignment graph for CTC is a little more complicated than for ASG, which is why I started with ASG, even though CTC is a much more commonly used loss function for speech recognition. The target alignment graph for CTC looks like this. So the semantics of this graph are that, say I have an output y equals AB, I can have a blank, any number of blanks in the beginning, but I have to observe the first output. Then I can have any number of blanks in between the first and second output, including 0, which is why we have this arc at the bottom. but I have to actually observe the second output. And then I can have any number of blanks at the end. But that also includes 0, which is why this is an accept state as well as this. Looks like there's a question. How hard would it be to implement RNN-T loss in the automata framework? So the RNN-T loss is actually quite tricky to implement with automata, and I'm not even sure it's possible. And yeah, it's hard. It's a bit difficult to explain why. So I'm gonna punt on explaining why. But the short answer is I'm not sure that it's possible to implement the vanilla RNN-T loss function in the CTC in the automata framework. So as a little question to the group, what does the alignment graph, sorry, I think we just did that. Okay. All right, so what is the alignment graph for y equals AA? So sorry, that must be a typo in the slide. Okay, oops, that should say y equals AA. So now since there's repeats in the output, we have to have the blank token between the two A's. So you notice the main difference is you have to go through the blank token from the first A to the second A. There's no longer that shortcut connection. Sorry, I'm hurrying now because we're almost out of time. I want to make sure people can get to their next events. So we're almost at the end. So CTC, if you look at the implementation, this is what it looks like. Now, I have a question. What is the difference from this code to transition-free ASG? Think about that for a second. And the answer is there is no difference. It's the exact same code. The difference in functionality comes from the graphs that we give this code as input. And you can see that, in fact, the only difference is in this target alignment graph, A sub y. So again, that really shows you the power of expressing things as operations on automata. There's a question, is there a common name for this generic ASG CTC function? Not that I know of. No, not that I know of. And that's it for the presentation. So before we conclude, there's a few resources that you might find interesting for those who would like to learn more about the the automata and the theory. I recommend this kind of companion tutorial that I've written about automata, which goes into more detail, but covers a lot of the same things. More examples. There's a research paper that I myself and some of my collaborators wrote, which shows some of the more cutting edge things you can do with the ideas of differentiable weighted automata. And then in the former as well, there's some references to even more works on learning kind of the deeper theory of automata. And for those with a more practical bent, I recommend GTN as a place to play around. You can download the code or spin it up in a Collaboratory Notebook. There's some documentation. And then kind of one of the best ways to learn is just by, constructing graphs, running the operations, visualizing the resulting graphs. Unlike tensors, one of the great things about graphs is that it makes sense to visualize them. So, GTN comes with a drawing function, which helps you visualize the graphs. It's how all the graphs in this presentation, or most of the graphs, were constructed. There's some final questions. Let me answer them really quickly. How would I train a neural network with these GTN losses? Yes, there is an example. You can find that example either by following this link and looking for the code link there, or I believe there is an example of how to integrate with PyTorch in the documentation as well. And then last question from Brian. Could you comment on the decision to implement GTN operations on CPU rather than GPU? That's not a decision. There's no dichotomy there. We'd love to do both at some point. We're working on GPU implementations at the moment. Okay. Thank you all for the questions. I think that's all the time we have.